Okay, actually, I'm gonna have to go in about like 10 minutes, so let's, you actually, let's not do this here, we can do that on the, you can see the solution for that. So let's do, so you could also need to do a discrete one, right? But we did it in class anyway. So let's do one. The other, what you're definitely going to get is going to be something like write the likelihood function, code something, write that table, and then do some decoding, right, for something. But we'll try to do that. So let's just do an example of what more like typical problem would be. So let's say that, let's take a code C1. Something stupid like this. Okay, this is like a stupid code. All right. All right. What is the rate? Okay. Okay. This is easy. What's the code rate? How many input bits are there? You take 2 bits in and you get 4 bits out. So the code rate is? Okay, half. All right. You guys need to review this. All right. Should I not do this? Do you want to wait to review this over the weekend and then I'll go over? Would it be better? Because I think I'm just going over everybody's head right now. The log likelihood ratio is really big as that's supposed to. Okay, so why don't we call it quits right now?
Can we finish this one?
Oh, okay, I'll just do this one.
Yeah, let's do
this
it.
one. Okay, so what's the code rate? Okay.
Yeah.
Suppose you transmit or modulate with 64 quad at 10 megasymbols per second. What is the information rate? Okay, so how do I do that? Well, the information rate will be R. I'm going to take the number of, yeah, exactly. I'm going to take the information bits by coded bits. Actually 6. Okay, coded bits per symbol, and then symbol per second. Right? All right. So in that information, that's 1/2. That's the code rate. How many bits are there per coded bits are there per symbol? There are 6. All right, because it's 64 quad. All right, and then it's 10 megasymbols per second. So this will be 30 megabits per second. All right. Okay, write the generator matrix for this code. Right, the generator matrix is really simple. You just want to basically write C, all right, which is C1, C2, C3, C4, as some B1, B2 times the generator matrix. Right? So I'm going to write that here as B1, B2. So C1 is just 1 times B1, C2 is, C3 is 1 plus 1, and then C4 is B2. Okay? So that's, does that make sense? So that's easy. So, I mean, your first 2 problems will be like this. They'll be really quite simple, all right? Maybe. Okay, suppose that,
Sandeep,
yeah.
how did you figure out G?
Oh, G, I looked at these equations here.
Yeah.
So C1 is B1.
Okay.
So if I want to write that, if I write, note that, right, C1 is B1 times 0 plus 0 B2.
Okay.
C2 is 0 times B1 plus 1 times B2. Alright, and then B1 plus B2 for C3, and 0 plus B2.
Just really quick, how do
okay.
you know that it's 6 coded bits per symbol in a
64 quant. 64 quant has 64 points,
Two,
or 2 to 6.
2 to the 6 is 64. Got it.
Yeah.
This has nothing to do with like a constellation diagram or,
I mean, it kind of does it, that if you were to draw that constellation at 64
or we don't
points,
have to.
nobody would have to draw the constellation diagram, correct?
It
You
could have.
to know this exactly.
It could have been possible that we have C1, B1, and C2, B2, and C3, B3, right? Or that wouldn't be.
Yeah, that's possible, then it'd be a different code. That means you're taking 3 input bits,
Okay.
right? It'd be a different code. It's perfect, then you could totally do that.
Okay.
And then G would have 3 dimensions.
Right, exactly. It would be 3 by 4 in that case.
Yeah. Okay.
Yeah, and then the code rate would be 3 quarters. All right. Okay. So, okay. Yeah, let's just do a quick thing here. All right. So, get symbols RI. Okay, say 0 or 1. Oh, okay. Yeah, let's just draw like this. Okay. All right, let's just write this. The probability okay. So basically, QI is the error probability on the ith symbol. All right. All right. Okay. So. So, suppose we receive, let's just say R is 1, 1, 0, 1. I don't know. I don't even know if that's a valid code word. Oh, yeah, it is a valid code word. All right, like this. All right. All right. Find P of R given C. Okay, so basically what I do is I write all the bits. This is where I do the table, right? B. So 0, 0, 0, 1. Right? Here's C. Right, so C is going to have 4. This will be 0, 0, 0, 0. All right? This one will be 0, 1, 1, 1, 1, 0, 1, 0, 1, 1, 0, 1. Okay, so you know that R is not exactly any of these three. Now, the trick here is I have to write what this is the only hard part of this table to do. So I want to find the likelihood of each bit. I'm going to do this, remember there's 3 ways to do it. I can do it in linear domain, I can do it in log domain, or a scaled log domain. I'm going to do it in linear domain, all right? So remember that R, all right? So, okay, so in this case, R is, I always write it like this. I put my R here, so I can remember. It's, what do I get? 1, 1, 0, 0, right? And the likelihood will be if the bit is, okay, so if I write now here, L of R given C, right? This is or P of R given C. So right here.
So did,
Yeah.
how did you get the last line of 110?
Maybe I mean which one?
Yeah.
1, 1. C4 is B2. So it's 1 plus 1, which is 0.
Right. Okay.
And then, yeah.
Got it.
Okay.
So I see the first 2 columns of C are just B, right? So 0, 0, 0.
Yeah, correct.
What about the last 2 columns?
That's coming from there. C3 is B1 plus B2.
Okay,
But remember, it's B1 plus B2 mod 2, right? So I take the first and second bit, so I take this plus this, which is 1, 1 plus 1, which is 1, 1 plus 1 is 2, but 2 mod 0 is, 2 mod 2 is 0.
okay, and then the last.
Last column is just B2.
Oh, okay.
It's really easy. It's like very, very easy to get this. You can get like most of the time. This is the only hard part. Okay, so in this case, R was 1, so the chance of getting this guy would be, this is an error, so the chance of getting this would be Q1. Alright? The chance of getting this guy would be, this is an error, this would be Q2. This is correct, so it would be 1 minus Q3. Alright? And this guy here would be 1 minus Q4. Does everyone see that? For each bit. Alright?
How do you know one's an error and one's not?
Because I received here a 0. Had this code word been transmitted, it would have also transmitted a 0. So that means that Ri would have equaled Ci. Alright, so that probability, so that means that the probability that Ri is equal to Ci is 1 minus Q1. Alright, so, because either, for a given Ci, it's either equal to or not equal. Alright, so, does that make sense now? So, you transmitted C3, and 0, we know we received a 0. Had you transmitted a 0, that would have occurred with probability 1 minus Q3.
1 not Q3.
Why? Because Q3 is the probability that they're not equal.
Okay.
Right? So basically in this case, for every time they're not equal, I put a Q1. So this one's Q1, alright, and this will be 1 minus Q1, 1 minus Q1. This will be 1 minus Q2, Q2, 1 minus Q2, etc. Alright? And then Q3, Q3, 1 minus Q3, and this will be Q4, 1 minus Q4, and Q4. And then, if you're doing it in the linear domain, you multiply these guys out. So P of R given C, all right, is Q1, Q2, all right, 1 minus Q3, 1 minus Q4, right, etc. And then I just multiply these guys out. Now then, if I gave you Q1's values, Q1 to Q4, you could pick which is the maximum one. But I don't know. So that's it's basically something like this will be your problem. So you know,
How do we fill out the last?
oh, you just multiply these guys.
Oh, okay.
So remember, there's 3 ways to do it. You can do it in linear scale, then you put the probability in each one, and then multiply. Do it in log scale, so you compute this log likelihood ratio. You put them in and then add, or scale log the likelihood, you also put them in.
Okay.
But this method is the linear.
This is the linear method. Alright, this is the linear method. Okay, we'll see you guys Monday.